Yes, good evening, students.
Good evening, ma'am.
Could anybody share a screen today? From Neiman, it would be, I would continue with the MOS capacitor part, that is chapter 11 in the PDF that you have. Chapter 11, and we start with article 11.1. If you could share the screen, it would save time. Otherwise, I would be drawing the energy band diagrams and proceeding in the usual manner. What would you like? Would you like to go on a sharing screen mode, or I would draw the diagram and explain as I do it? I have no objections, but I'm only with both. Any special suggestions regarding the options? কিছু বলবে কোনটা করব? তাহলে আমি অসুবিধে নেই, I'll draw it and let you explain. Fine. Okay, so we have discussed JFET, MOSFET, drain transfer characteristics, phenomenon of pinch-off and things like that. So more or less, we have discussed the devices. But now what we would be concentrating on mostly is the metal oxide semiconductor part of the MOSFET. The MOS part of the MOSFET, that is the metal oxide, that is SiO2 layer and the semiconductor layer. And we would be studying certain properties, or rather certain characteristics related to this MOS structure. So before we go on to this detailed characterization of the MOS, we need to understand certain phenomena which are related to this MOS structure. So I proceed to it. It would be again directly chapter 11 from the PDF that you get from Neiman, or it would be chapter 10, that is the two-terminal MOS structure. That's the name of the chapter, the two-terminal MOS structure. That is chapter 10 if you are using the hard copy, that is the book itself, and it would be chapter 11 from the PDF of Neiman. Okay. So now, what was the matter? If we just concentrate on the MOS part of the device, so you have the semiconductor substrate. So this is the semiconductor substrate. This is the semiconductor substrate. Okay, this is the semiconductor substrate, and then you have the oxide layer. This is the oxide layer, the SiO2 layer, the oxide layer, and on top of is the metal coating part. That's the metal. That's the metal part. That's the metal part. Okay, that's the metal part. And this is OX stands for the oxide layer. It is the permittivity of the oxide layer. Epsilon OX is the permittivity of the oxide layer, and this is the thickness of the oxide layer. TOX is the thickness of the oxide layer. So this is basically the MOS structure that we are concentrating on, the MOS structure of the MOSFET that we are concentrating on. And whatever we have discussed right now, whatever till now we have discussed is we talk about a p-type substrate. We talk about a p-size substrate so that the device would become an n-channel device. Okay. Now, you know that capacitance is defined for a parallel plate capacitor if epsilon is the permittivity of the medium, or in this case, epsilon is the permittivity of the oxide layer. So you have the capacitance of the capacitance of this geometry, which is drawn on figure, is epsilon A by D, where A is the area of cross section and D is the thickness. Okay, in general terms, epsilon A by D. So capacitance per unit area, that is C by A, we call it C dash or C prime, that is equal to epsilon by D, that is equal to epsilon by D, that is equal to epsilon by D, that is equal to epsilon by D. C dash is equal to epsilon by D. So epsilon A by D, that is equal to epsilon by D, that is C dash. Okay, so you have, this is the basic equation for the capacitance per unit area, and you have Q dash is equal to C dash V. Q dash is equal to another equation, that is, since we are dealing C dash as the capacitance per unit area, then we can also write the magnitude charge per unit area as Q dash is equal to C dash V, where V is the potential difference, and you may also write an equation for the electric field E. Electric field E would be equal to V by D, is equal to V by D. Electric field E would be equal to V by D, E equal to V by D. Okay, so Q dash is equal to C dash V and E is equal to V by D. Q dash is equal to C dash V, E is equal to V by D. Fine. Okay. Is it clear? Is it clear, students? Is
Yes,
it
ma'am.
clear, students?
Yes, ma'am.
Fine. So this is about the general geometry. Okay, this is about the general geometry. Now let us see. We would be discussing three phenomena with case of this MOS capacitor. That is, one is accumulation, second is depletion, and the third is inversion. Okay, let us go in for the first phenomena. Okay, so the first thing that we are very much familiar with in case of our MOS structure is, I will have to redraw this diagram again and again for the sake of explanation. So if you're taking a p-type substrate, this is the oxide layer, and the metal layer, taking out terminals for electrical connection, and if you place a negative charge on the metal plate, if you place negative charge, this is the p-type substrate, this is the oxide layer, this is the metal, and this is a negative variable battery used, and a negative positive polarity use means, negative positive polarity use means what? This is having, this upper part of the metal plate is having negative charge, the upper part of the plate is having negative charge. So when you are having negative charge on the upper plate, what is going to happen? This is the p-type substrate, this is the p-type substrate, this is the substrate which is p-type, this is the p-type substrate. Okay, so whenever you are giving a negative charge, what is going to happen? The holes are going to be attracted towards the negative terminal of this metal, and there would be attraction for the holes, there would be attraction for the holes, and there would be accumulation of positive charge at the junction of the metal, the oxide semiconductor interface, at the oxide semiconductor interface. This is the oxide, this is the oxide semiconductor interface, right? So at the oxide semiconductor interface, there would be accumulation layer of positive charges or holes. You call this accumulation layer of holes. You call this accumulation layer of holes. Fine. You call this what? Accumulation layer of holes. You call this accumulation layer of holes. So that would give you the phenomenon called accumulation. That would give you the phenomenon called accumulation. Okay. Is it clear? Is it clear?
Yes, ma'am.
Okay, fine. So the energy band diagram, we would go in for the energy band diagram for the accumulation layer, for the accumulation condition. I'm rubbing out the structure that we have here. Okay, I'm rubbing out the structure that we are having here, and I'll be drawing the energy band diagram. Okay, now let me first draw the diagram and then I would be explaining. I'm drawing the same diagram vertically. So you have the gate, this is the metal, this is the oxide layer, this is the oxide layer, and this is the, suppose, p-type substrate that you have. This is the p-type substrate that you have. So we are trying to draw the energy band diagram. We are trying to draw the energy band diagram for a mass capacitor with P substrate when a negative potential is given to the gate. When a negative potential is given to the gate. So since there is an oxide layer, since this oxide layer, as we discussed while we studied MOSFET, acts as an insulating layer, there is no flow of current between the P substrate and the gate terminal, accounting for the very high impedance of the gate terminal, right? So since there is no flow of current, even when a negative charge is applied at the gate terminal, we call the junction to be at equilibrium because there is no flow of current through the oxide layer into the gate. So in order to understand the energy band diagram, the first and foremost thing that we keep in mind, as we had done in case of our PN junction as well, is that the Fermi level, in this case, since it's an extrinsic semiconductor, the extrinsic Fermi level, I'm drawing in red, the extrinsic Fermi level the extrinsic Fermi level would maintain a constant level throughout the material, in this case the oxide and the semiconductor, okay. Now since it is a p-type semiconductor, what is going to happen? As we all know that, I'm drawing in blue, the valence band will be closer to EF The valence band, the blue one, the valence band will be closer to EF. Redrawing it again. The valence band would be closer to EF, that is EV is the valence band, compared to the conduction band. Compared to the conduction band. This is a very old concept that we have been discussed since our starting classes with ED. Okay, so this is EC, this is EV, and this is EF. And intrinsic Fermi level, I'm drawing in black, that must maintain the equidistant position from the conduction band and valence band, that I'm drawing with a dotted line, that is EFI, intrinsic Fermi energy level. So that is the location of the energy bands of the p-type substrate when you have applied a negative potential, but just suppose when you have not applied a potential, this is how the band structure would look like. Okay, this band structure would look like. Fine, this is clear with all of you. EF is the extrinsic Fermi energy level. EV, since it's a p-type semiconductor, 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 what happens? The valence band would be closer to the extrinsic Fermi energy level. The conduction band would be lying away from the extrinsic Fermi level, and the intrinsic Fermi level would be midway between the conduction band and the valence band. Okay, so that is drawn as EFI. Fine. Now, when you apply a negative charge, what happens? When you apply a negative charge, there is accumulation layer of holes created. There is accumulation layer of holes created. Accumulation layer of holes created over here. Right, accumulation layer of holes created at the oxide semiconductor interface. So what is going to happen? What is going to happen? Since there is accumulation of positive charge as the oxide semiconductor interface, it is as if at this interface region, it is as if at this interface region, it is as if at this interface region, the semiconductor becomes more p-type. The semiconductor becomes more p-type. So as if at the interface between the oxide and the semiconductor becomes more p-type. The semiconductor becomes more p-type. So what do you do? What do you do? If the semiconductor becomes more p-type, how do we represent it? The more p-type, the more will be the valence band going closer to the Fermi energy level. The more the valence band will be moving closer to the Fermi energy level. So this energy band structure will undergo a slight modification in the form is, you see, in this region, the Fermi level will be closer to the, sorry, I'll use blue ink as before, or the valence band. Okay, so in this region, since there is accumulation of positive charges in this region, accumulation of positive charges in this region, the region becomes more p-type, so the valence band moves up closer to the Fermi energy level. And similarly, you have the bending of the bands in case of your conduction band as well. The conduction band moves up a little bit away from the Fermi energy level, and therefore the intrinsic Fermi energy level maintains its property of being equidistant from the conduction and the valence band. Therefore, it too takes a curved structure like this. So this is band bending. This is band bending. We'll see this. We missed Schottky barrier diode. I would be going, since I've started on with the MOS part, I'm trying to complete this. This is basically module 4 of your syllabus that I'm doing. So I would be trying to wind up the syllabus by next week, means first week of March. I would wind it up, and then maybe bits and pieces of things would be left. I would be left with I have still, whatever I remember, I have continuity equation left from module 1. I have Schottky barrier diode and small signal PN junction diode module 2. So this would take another 3 classes. Okay, this would take 3 topics, around 3 classes, approximately 3+ classes, minimum 3 classes. Okay, that's what we are left with. I have started MOS today. If I am taking class till 7:30, then maybe another class tomorrow, another 1 hour class tomorrow might complete the chapter. So that would be 4 classes more to complete, 4 or 5 classes more to complete this, and 2 classes to be discussing a little bit of transistor characteristics have already been told to you while discussing the practicals. Little bit of that, and some transistor modeling part is left, that is Ebersmol and things like that. So another, I think, 5 6, another 8 classes. So approximately from tomorrow, if we are doing 6, at least 6, maybe 1 or 2 extra classes in the middle, around 8 classes required to complete your syllabus, the major chunk. And then if we proceed with the classes, I can discuss question answers, revision, and anything of that sort. And for the laterals, there would be still a few more classes. So that is the way I'm working with. So let's proceed. Fine. So this is how this is called band bending. This is called band bending, and this band bending I have discussed is when you have given band bending, when you have given negative charge at the gate. Is it clear how the band is bending? This is straight away from Neiman. So if you follow the chapter today after I take the class, things will become more clear to you. Is it clear, students? Is it clear? Energy band diagram, energy band
Yes, ma'am.
bending in case of MOS with P substrate when a negative potential has been applied to the gate. Clear? Fine. Okay. The next thing that we would do is with the same MOS structure, if we apply a positive potential to the gate terminal. So what is going to happen? First, let me draw the physical structure. So this is the same P substrate. This is the oxide layer. Okay, this is the metal part. Okay, and what you're doing is, instead of giving the negative charge, if you are giving a positive potential to the gate terminal. If you're giving positive potential to the gate terminal, so what you're essentially doing is, this entire metal plate becomes positively charged. This metal plate becomes positive charge, and what you are doing is you are actually repelling the holes. Since this is positive, the majority carrier holes are being repelled. Into the p-type substrate, and it is as if a layer of negative charges, and it is, since it is repelling the negative charges, means it is repelling the holes, means what? As if a condition similar to the buildup of your depletion layer in case of our p-n junction that we had seen. It is as if there is an induced space charge region over here with negative charges, or you may also think it to be the other way around, that it is also pulling, as we had discussed in case of our MOSFET. The both concepts are the two ways of thinking the same thing. That is, as if you have attracted negative minority carriers from the p substrate, and it has accumulated over there. Giving a layer of, it is called a layer of induced space charge region, we call it, for a little moderately or moderate to low applied positive charge at the gate. For moderate to low applied charge at the gate, what you do is you are actually leading to the accumulation of negative charges. Okay, so that is giving you induced space charge region which is negative. Now if this positive charge is still larger, we will see what it happens in case 2, case 3. So case 1 was accumulation, case 2 was as if induced space charge region, where you have negative charge accumulating on the p-type substrate or at the boundary of the oxide and the p-type substrate. So let us see how the energy band diagram looks like. Tomorrow we are having practicals in the morning, right? As we have 10:30 onwards, 10:30, 11, whatever time teachers are available. Okay. So what would be the energy band diagram like? So what we have is, first we start on with the same notation. Since there is no current flowing, we assume that the extrinsic Fermi level maintains a constant level throughout, maintains a constant level towards the in the P region, in the entire P region. So that is EF, or the extrinsic Fermi energy level. Okay, and now what happens? There is accumulation of, we say, negative charges. There is accumulation. This is a p-type substrate, no doubt. So when suppose we have not given any positive potential, then what would be the energy band diagram like? So EV, since it is a p-type substrate, EV would be lying near to EF, EC would be lying away from EF, okay, away from EF, and EFI would be lying midway. EFI would be lying, I would be using black for EFI, okay, so EFI would be lying midway between, EFI would be lying midway between EV and EC, EV and EC. Fine. So that is the normal distribution of your energy level, EC, EV, conduction band edge, valence band edge, intrinsic Fermi level, and extrinsic Fermi energy level. Okay. Now what happens is, if we are applying this positive charge, which I erased, if we are applying this positive charge, then what is going to happen? As we said, that near the oxide semiconductor interface, there would be rather creation of a negative space charge region, or an induced space charge region with a negative charge. So the minute this region near the interface becomes negatively charged, what happens? It is having an excess of electrons, that is, it is having, like the way we said that we are inducing the channel, so it is leading to the accumulation of negative charges over there. Means what? The material is becoming less p-type and more of n-type. So if it is more of n-type, then we will see that the conduction band edge and the valence band edge are changing in this fashion. In the bulk semiconductor, EC is as it was before, but as you are moving close to the interface, that is oxide metal interface, there is a tendency of EC to move closer to the extrinsic Fermi energy level, because there is more number of electrons over there. And since this is the case for EC, so and the material is becoming less p-type, the valence band is having a tendency of moving away from the extrinsic semiconductor, from the extrinsic Fermi energy level in the oxide semiconductor interface. Similarly, the intrinsic Fermi energy level Similarly, the intrinsic Fermi energy level the intrinsic Fermi energy level, okay, would also have show its property by being equidistant, by being equidistant from the conduction band and the valence band edge, and it also bends in this fashion when you have a minor accumulation of space charge. And this region of the bent, something similar to that of your depletion region created, as we say, we call this XD, this dimension as XD, or it is called the induced space charge region. Induced space charge region. Induced space charge region. That is when you give a small positive charge to the gate. When you give a small positive charge to the gate. Okay. So that is called how that shows how there is accumulation of the negative charges at the oxide semiconductor interface. This is the semiconductor, this is the oxide, and this is basically the oxide. I'm blackening it. This is basically the oxide semiconductor interface, and there is bending of this energy band at the oxide semiconductor interface. Is it clear, students? So we have discussed two parts. One is your negative charge, that is accumulation. The other is induced space charge, that is very mild form of positive charge applied to the gate. And 26 people right now. Is it clear to you, students? Is it clear to you, students?
Yes, ma'am.
Yes, ma'am.
Okay, fine. What about the rest of the people? It's 26. I understand it's Sunday, but I took your consent and then I set up a class because I missed quite a few classes from the last few weeks because of network issues, because of my personal problem. So maybe that's why I thought of it. I thought it could be done yesterday, but somehow again I had issues at home, so I couldn't make it up. So today, therefore, I made it a point that even it's Sunday and if you people are willing, then I could take a class. Yes, 26 of you are willing, but what about the rest? I don't know. Maybe I could talk about it tomorrow in the lab. Lab attendance is much better, but if you're able to manage it on your own, then I'm very happy. But only one request to you students, please don't land up with a supply, because I just see that it's people who do not attend classes are the people who get supply. Though getting a supply is difficult, but still you manage to get it. Okay, and it's statistics says for my years of teaching in this college that it is the people, it is not the people who do not understand who get supply, but it is the people who do not do classes get supply. That is what I have seen. So you are attending the class, no point talking to you about this, but 26 is attending in a huge class. So what is your strength right now? 63 plus the laterals. How much is your complete strength right now? 70 plus, right? Exact strength, Sunitra?
72, 73, like that.
72, 73, and 26 people are doing the class. So I don't know. Is this the scenario in all other classes?
Yes, ma'am, almost.
Yes, ma'am.
Almost. Today it's Sunday special 26, I understand. So your highest attendance these days are 31, 32, 33, not more than that.
Yes,
Not
ma'am.
more than that.
Like all within 35.
In all classes, right? Signals, AB sir's
Yes,
class, in all
yes, yes,
classes.
ma'am. Yes, ma'am. Yes, ma'am.
Okay. I don't know what is the issue, Mane. What is the problem? Is it network problem, or you have people have lost interest? Okay, I'll catch you people in the lab tomorrow, because that is the place where people are present. Theory is nonsense, and at least lab makes a little bit sense. So next tomorrow's will be something different, sort of a practical. Let's see what I can do. Maybe I will teach the related theory of that in a theory class to see whether the attendance is pulling up. Fine. It's a holiday for you, it's a holiday for us even. So we really don't like sacrificing our holidays, but it's responsibility that I've missed a few classes and it needs to be made up. So I don't know what is the cause of such poor attendance. Your class was very sincere with the attendance, and I told people also that this batch is very good with the attendance and very particular about joining time and things like that. But since the last 1.5 months, I see, and in online mode, you just can't bring back any discipline also because you keep on joining, you keep on leaving. মানে দেখো পড়াবো না এইসব মনিটর করবো মানে I hate concentrating on cosmetics. In fact, ওই attendance, কে কখন ঢুকছে, কে কখন বেরোচ্ছে, ঠিক আছে, কজন ক্লাস করছে, কজন ক্লাস করছে না, মানে এইগুলো জিনিসে যদি if I have to keep on concentrating, then আমার তো পড়ানোর অসুবিধে হবে। এই 50 মিনিটের ক্লাস সেট করি, তার মধ্যে যদি এইগুলো করতে থাকি, তাহলে ওখানেই প্রায় 10 মিনিট চলে গেল, left with 40 minutes। কি পড়ানো হবে বলো? দেখো it's up to your responsibility. One request, বাবা সাপ্লি পেও না, সাপ্লি পাওয়ার মতো পড়াশোনা এখানে হচ্ছে না। So don't land up with that. Manage to get a pass mark. Please study on your own. I feel that you are much more intelligent than what I am delivering to you, so that you can make it up on your own. সেইভাবেই আমি আমার মনকে মানে সান্ত্বনা দিচ্ছি that is that you're intelligent enough to make it up on your own. Because I see quite a few students who are very regular also, they are not right now. I'm not mentioning their names, but যারা রেগুলারলি ক্লাস করতো তারাও ক্লাস নয় কেন? প্রবলেমটা কি? মানে ইজ ইট বিকজ অফ ল্যাক অফ ইন্টারেস্ট? আমরা কি খুবই খারাপ? আমরা না, আমি অন্তত আই ডোন্ট ওয়ান্ট টু জেনারেলাইজ ইট। আমি কি খুবই মানে নন ইন্টারেস্টিং বা খারাপ করে কিছু পড়াচ্ছি? তাহলে সেটা তোমরা বলতে পারো, কিন্তু সেটা বলতে পারো যে ম্যাম উই ডোন্ট লাইক ইউর মোড অফ টিচিং, বাট দিস ইজ নট দ্যাট। কিন্তু সব ক্লাসেই অ্যাটেন্ডেন্স এরকম হলে আই ডোন্ট নো, ইট মাইট বি আ কমন প্রবলেম। If you have any issues with my way of teaching and things like that, you can always come up to me. সামনাসামনি পড়ালে হয়তো বুঝতে পারছি that I have no issues listening to your feedback, because I feel more happy when you criticize me rather than when you praise me, because praises give me no room for improvement, but your criticisms do give me room for improvement. So I gladly accept it. So if you have any issues, no madam, this is not the way we like it. If you need to have a good way of saying it too, মানে একটু ভালো করে বলবে যে ঠিক আছে, যে এটা না হয় এটা হলে ভালো হয়, মানে instead of complaining, you can say that this is the way it's happening, এটা না করে এটা করলে হয়তো আমাদের একটু সুবিধে হতো, then maybe I would try to rectify myself. If you have any issues of that, so it's fag end of the syllabus, maybe it's 8 more classes to do with you. But still, if you have any suggestions regarding my way of teaching, online is very difficult with this subject, and therefore I did not believe in giving you any PPT presentations, because that would be mere copy paste from the books and that would be highlighted. So I felt that this drawing on board is much more effective. If I was a student drawing on board, and this in steps, in stages, you are facing the facts, that is much more helpful than I put a fixed diagram on board and tell you that this is this and this is that. হাতে এই যে আঁকছি তোমার সামনে, maybe it's not a very good looking one, because I'm drawing it with my finger on a screen. So that is, but I think that gives you at least 80% of the effect that I used if I used a chalk and on board. So that is the way I do it. If you have any suggestion, সেটা আমাকে বলতে পারো। আমি জানি না কিসের জন্য অ্যাটেন্ডেন্স এত কম। Anyways, এটা আমাদের কাছে খুব খারাপ লাগে when we are taking consecutive classes and we are taking pains to explain the syllabus. Syllabus এত সহজও নয় যে আমার মনে হয় you could do it on your own, on new concepts। জানি না কি করে মেকআপ করবে। আমি স্টুডেন্ট হলে তো পারতাম না। Anyways, so if you go in for a large positive charge, that means if you are giving a large positive charge at the gate terminal, that means if you are giving, I'm not drawing the diagram, I'll straight away go to the energy band diagram. So if you are giving a large positive charge at the gate, then what is going to happen? There will be more accumulation, or there will be more negative charges coming near the oxide semiconductor interface. So in that situation, the energy band structure
This is the metal, this is the oxide, this is the semiconductor. In this case, it is a p-type semiconductor. And if you are giving a positive charge, okay, if you give a large positive charge, I write it here specifically. If you give a large positive charge, then what is going to happen? Okay, so again, extrinsic Fermi energy level maintains a constant level. Now, what is going to happen? What is going to happen? Since there will be large number of accumulation of negative charges, so what is going to happen? The valence band is going to move at the interface. The valence band is going to move, just a second. The valence band is going to move very much closer to the extrinsic Fermi energy level. Similarly, the valence band would move very much away from the extrinsic Fermi energy level, and the intrinsic Fermi level would also bend in such a manner that now you see that at the interface, the intrinsic, this dotted black line that I'm drawing, this is EFI. This is nothing but EFI, okay, EFI, or the intrinsic Fermi energy level. So you see at the interface, the intrinsic Fermi energy level is lying below the extrinsic Fermi energy level, which was not the situation when we had applied zero bias to the gate. And in such a situation, there is accumulation of negative charges. There is accumulation of negative charges, and this is what we call is there is a layer of negative charges accumulating near the oxide semiconductor interface, and this is called the inversion layer of electrons. This is called the inversion layer of electrons. This is called the inversion layer of electrons. Okay, this is called inversion layer of electrons. Okay, and this now gives you XDT. There is as if the same situation as the thickening of the depletion layer, because lots of negative charges has accumulated in the oxide semiconductor interface. Okay, so this is inversion layers of electron building up at the oxide semiconductor interface, and you are having band bending. Is it clear, students?
Yes, ma'am.
Okay. Next is we would be concentrating on this large positive charge at the gate, that is quite a high accumulation of negative charges on the interface between the oxide and the semiconductor, and we'll define a condition which is very, very important and often asked to you in your examination. What is the threshold inversion point? And something which is analogous to the threshold voltage that I had discussed, that it is only when the threshold voltage is exceeded will there be current flowing through the device. That means the channel formation is complete and there is adequate number of accumulation of electrons or n-channel electrons that is sufficient to lead to the flow of current when a drain to source voltage is applied. Okay, so that is the same threshold voltage which we define from the condition of this band bending. Okay, shall I proceed? Okay, it's WebEx has already given me a signal with the first meeting, so it is going to get disconnected in no time. We are supposed to end at 7:05, so 7:10. So what I do is maybe let's join the next meeting. Maybe I'd pull for another 10-15 minutes and end it up with this part. মানে আমি এই threshold voltage টা explain করেই আজকে শেষ করব. So I think Sunetra, have you taken the attendance? It's 29. It's 29. If you take the attendance.
Although I've taken the attendance.
Okay, fine. Then what I'm doing is I'm disconnecting this. I'm joining the next meeting. You people join the next meeting and we go in for the continuation. Okay, fine.
Okay, ma'am.
Ma'am, can you repeat the name once? That threshold inversion.
কোন নামটা গো?
ম্যাম আপনি একটু আগে বললেন না থ্রেশহোল্ড ইনভার্সন কিছু একটা ছিল ম্যাম, ওখানে আপনার ভয়েস কেটে গেল বলে শুনতে পেলাম না।
ও আচ্ছা, threshold আমি ওটাই ডিসকাস করব এখন পুরোটা। threshold inversion point and threshold voltage.
ওকে
ঠিক আছে, threshold inversion point, I'll tell you the figures from Neiman. Don't worry, আমি এটা পড়িয়ে নি। Page numbers won't be matching. If you have the hard copy, maybe I could tell you the page numbers. Soft copy সাথে মিলবে না, but figure numbers I would tell you which you're supposed to refer. অসুবিধা হবে না।
ম্যাম হার্ড কপি পেজ নাম্বারটা বলে দিন, বই আছে আমার।
বই আছে, হার্ড কপি ভার্সন যদি ম্যাচ করে 434 খোলো, পেজ 434, ফিগার 10.9।
ওকে ম্যাম।
পেয়েছো the energy band diagram of a p-type semiconductor at the threshold inversion point? পেয়েছো ছবিটা? যাদের বই আছে খুলতে পারো। হ্যাঁ ঠিক আছে না, আমি আর 1 মিনিট ওয়েট করব, দিয়ে স্টার্ট করব। আজকে none of the lateral students are here today. আমি তো কোনো lateral student কে দেখতে পাচ্ছি না। What is the issue? Are they having any class?
I'm here. Ma'am, I'm present.
জয়শ্রী আছো? হ্যাঁ রাইট, জয়শ্রী আছো। আর বাকিরা তাহলে তো ক্লাস নেই। বাকিরা কোথায় গো? আগের দিন তোমাদের জিজ্ঞেস করলাম এক্সট্রা ক্লাস করবে কিনা, সেটাও তো জানালে না। দেখো, ইফ ইউ আর নট ইন্টারেস্টেড, ওয়াই শুড আই বি এট অল? ওই রুটিনে একটা ক্লাস লেখা আছে, আমি ওই একটা ক্লাসই নিয়ে যাব, তাতে আমার হয়ে যাবে। তোমার তো তাতে হবে না। আমি তো বলেছিলাম একটু জানাতে যে তোমরা মাঝখানে এক্সট্রা ক্লাস করবে কিনা, আমি ঠিক টাইম অ্যাডজাস্ট করে করিয়ে দিতাম।
আচ্ছা ম্যাম, ওদের আরেকবার জিজ্ঞেস করে আমি জানাবো।
আর আজকে জিজ্ঞেস করে লাগবে, আজকে আর সম্ভব নয় নেওয়া। কালকে আমার জ্যাম প্যাক শিডিউল থাকবে, তোমাদেরই ক্লাস থাকবে, অন্য ক্লাস থাকবে। একটু উইকেন্ডস গুলোই ফ্রি ছিলাম বলে, থাকি জেনারেলি, সবাই থাকে, জিজ্ঞেস করেছিলাম। আর আবার নাও अगेन ইউ হ্যাভ টু ফল ব্যাক টু দ্য কারেন্ট নরমাল শিডিউল।
ওকে ম্যাম।
যখন জিজ্ঞেস করি আমি তো আগের দিন ক্লাস নেওয়ার পরই তোমাদের বললাম, বরং আমি ওদের আগের দিন জেনারেল ক্লাসটা আমি স্কিপ করে তোমাদের নিলাম যে খানিকটা তোমাদের এগিয়ে দিই, তারপরে ওটা অ্যাব্রাপ্টলি ওয়েবেক্স কেটেও যায়, কিন্তু তারপর ইউ পিপল ডিড নট কমিউনিকেট। একটা তো বলতে পারতে, আমি তো জিজ্ঞেসই করেছিলাম যে আর এক্সট্রা ক্লাস করবে কিনা, এর মধ্যে আমাকে জানিও।
ম্যাম কেউ রেসপন্স করেনি তো আমি আর কিছু বলতেও পারিনি ওই জন্য।
ঠিক আছে, যদি সবাই না করো, দু একজন, তিনজন, চারজন করো, আগের দিন তো অ্যাটেন্ডেন্স কমই ছিল, সেটাই করবে। যারা ইন্টারেস্টেড তারা পড়বে, আর যদি কেউ না করো আমি বুঝবো আমার দরকার নেই, আই ডোন্ট হ্যাভ টু বদার, ইউ ক্যান ম্যানেজ ইট অন ইউর ওন, ফাইন, আমার কোনো প্রবলেম নেই, অ্যাজ লং অ্যাজ ইউ আন্ডারস্ট্যান্ড আই এম হ্যাপি। Okay, so continuing with what we were discussing, that is if the positive potential on the gate is very much increased, if the positive potential kotota increased hobe, let's see, that we will define from ami boite kichu equations so bole debo, you just go through it, they are your known equations which we had derived earlier in our PN junction. Okay, those like barrier potential type of equations, I would be using one equation here, but equations, derivations, you don't have to go in. Final expressions are given in this chapter, you can go through it. I'll mention the equation numbers later. Let me give you the concept first. Now I'm drawing this diagram first, the energy band diagram first, and then I will explain what is happening. Okay, so now if you give a very high value of, listen, I'm not drawing this diagram, physically trying to understand what is happening. If you are that same diagram what we had, acha, I'm drawing it a bit for you. So this is the metal, this is the oxide, and this is the semiconductor, this is the MOS structure. Okay, and if you're giving a this is the gate terminal, if you're giving very, very large value of positive potential over here, so what is going to happen, there will be large number of negative charges accumulating. And remember we said that when we were discussing the device, the MOSFET actually, then this very high value of negative charge required just for the conduction of drain current to take place is called the threshold voltage. So from this MOS energy band structure, we are trying to define such a condition. Okay, we are trying to define such a condition. So let's go back to the energy band diagram. Fine. So this is the metal, this is the gate, this is the oxide. Okay, and if this is the P substrate, if this is the P substrate, then if you have a very large positive charge, very large positive charge, very large positive charge, I call it very large positive charge. Okay, what happens is, let's start with the extrinsic Fermi energy level. Let's start with the extrinsic Fermi energy level, which maintains a constant level throughout the device. Fine. And now, when there is a very large positive charge, there is large accumulation of electrons near this. This is M, this is O, this is S. There is large accumulation, I'm using a yellow pen, there is large accumulation of negative charges in this metal oxide interface. Fine. So if there is such high accumulation of charge, then what is going to happen? There will be large number of negative charges accumulating. So at that yellow region, that is the oxide semiconductor interface, the device becomes, or the substrate, this P substrate becomes more N type, more N type. So what is going to happen? There will be large bending of the conduction band, and conduction band will try to move to the extrinsic Fermi energy level. This is your EC. Fine. Similarly, the valence band will move very much away from the intrinsic Fermi, so from the extrinsic Fermi energy level when you come to the interface. Fine. And accordingly, intrinsic Fermi energy level will maintain its equidistance property from the conduction band and the valence band. This is EFI, EFI, this is EC, okay, and this is EF. Fine, this is EV, sorry, that is EV. I wrote EC by mistake. That is EV. This is EC. Fine, so this is how the structure looks like. Now, let us discuss this threshold condition of operation. In this threshold condition of operation, this is the bending that has taken place. Okay, so this thickness we called as XDT or XD threshold, okay, and this is the distance between the intrinsic Fermi level and the extrinsic Fermi level is called phi fp, is called phi fp, is called phi fp. This distance between the extrinsic Fermi level and the intrinsic Fermi level is called, as we have discussed earlier, E phi fp, E phi, okay, fp, E phi fp. Fine, this is called E phi fp, okay, and the distance between the, let me draw it and then I'll tell you. The sorry, not this, the intrinsic Fermi level. I'll redraw it, don't worry. The distance between the intrinsic Fermi level, this is in the bulk material. This is in the bulk material. You call it bulk because it is far from this interface, far from this interface. So the distance between the, or the space gap between the intrinsic Fermi level in the bulk material and at the interface, this magnitude, it is called the surface potential, or E phi s. It is called the surface potential, or E phi s. E phi s. It is called the surface potential, E phi s. Okay, and the condition that for very large value of positive potential given to the gate, okay, very large value of positive potential given to the gate, when this surface potential E phi s is twice the value of E phi fp, let me write it on top. I'm just erasing the words MOS. I'm using yellow colored pen to write down the equation.
I'm using yellow colored pen to write down the equation. Okay, when this E phi S is equal to twice E phi F P, that is the condition when this E phi S is equal to twice E phi F P, that means this spacing is twice of this spacing. We say that it is the threshold inversion point. We say that it is the threshold inversion point. We say that it is the threshold inversion point. It is the threshold, where to write? It is called the threshold inversion point. It is called the threshold inversion point. It is called the threshold inversion point. And applied gate voltage, and this applied gate voltage, creating this condition is known as the threshold voltage, like we studied in case of our MOSFET. Okay, so in order to achieve the condition that phi fs, E phi fs is equal to twice E phi fp, okay, where phi fp, E phi fp is the distance between the intrinsic Fermi level and extrinsic Fermi level in the bulk material, okay, and phi fs is the surface potential. It's called the surface potential. It is the distance between the intrinsic Fermi level in the bulk material and intrinsic Fermi level at the interface, oxide semiconductor interface, that is E phi s. So when E phi s is twice the value of E phi fp, you get the threshold inversion point, and at that threshold inversion point, the applied positive gate potential is called the threshold voltage. And what is the significance of this threshold voltage? Threshold voltage is the voltage where a significant amount of accumulation of negative charges has been taken place on the oxide semiconductor interface, so that a nice induced channel of negative charges has been created. And now with the application of a positive drain to source potential would lead to the flow of current in the device, a drain current in the device. So this is called the inversion point or threshold inversion point and threshold voltage. Is it clear, students? It is figure 10.9. The explanations I have given pertaining to what we were discussing, but this figure that I have drawn over here is the same as figure 10.9 from your hard copy, and I think it would be 11.9 from your soft copy. Just give it a check. Just give it a check and go through the few. We have discussed this phenomenon, and a few underlining equations are mentioned in the book. That is equations 10.4, 10.5, and 10.6. Just go through them. Just go through them. You'll understand. That means once gives you the expression for this x dt that I had drawn. That means the thickness of the depletion width. The other is the expression for phi fp. Okay, x dt and phi fp. Just go through those expressions. They are known to you because those same equations were derived for you, and we had discussed that in details when we had discussed the p-n junction. Okay, the thickness of the depletion region, okay, barrier height and things like that. Okay, so those are known equations. Is it clear, students? I won't be extending anymore. The rest of the chapter would be completed tomorrow evening, maybe in that 6:30 as we do it after AB Sir's class. If any changes, we could talk about it later, but I don't think tomorrow we'll have changes. I'll complete it tomorrow by 7, 6 to 7. I'll be taking a single class and completing this part. So tomorrow we would be discussing flat band voltage and a little bit of CV characteristics. Okay, so that would more or less end your module 4. So is it clear, students? দেখে মনে হচ্ছে অল্প পড়ালাম, বইতে কিন্তু অনেকগুলো পাতাই পড়িয়ে দিয়েছি. You have to read through it, maybe around 7, 8, 1, 2, 3, 4, 5, 6. Around 8 to 10 pages I have taught you. So the same explanation is given with respect to your n-type substrate also in the book. If you're interested, you may go through it. Things would just be the reverse. Where you're getting positive charge, positive gate potential, there you would have to apply negative gate potential, and the band bending would be changing just in the opposite manner as was happening in case of your p-type substrate. Okay. Any queries or anything to say? 25 of you out here now. Any queries? কিছু বলবে? হ্যাঁ বলো
Ma'am, you
রাহুল।
said that there is a significance of threshold voltage, and after that, what you said, I could understand. So, ma'am, can you please repeat it?
হ্যাঁ, the significance of threshold voltage মানে এটা তো বুঝলে ডায়াগ্রাম থেকে how we defined surface potential phi s and phi fp, ওটা বোঝা গেছে।
Yes, ma'am. Yes, ma'am.
And you also got it that the threshold inversion point is defined as the condition when the bending of the energy bands would take place in such a fashion that E phi fs is equal to twice of E phi fp. That you understood? Okay.
Yes,
So
ma'am.
that condition is called when band bending would take place in such a such a magnitude so that E phi fs is equal to E phi fp. You call it threshold inversion point. And the how do you define threshold voltage? And in order to obtain this threshold inversion point, you had applied a certain value of positive gate potential. Okay, that is called the threshold voltage. And physically, what do you mean by threshold voltage? This is what we are discussing is with respect to that simple MOS capacitor. Okay, now if you extend this concept to the device, because this MOS capacitor is the heart of the MOSFET, so we are just taking out as a filtering the MOS part, and we are studying it. But we have the total MOSFET in amalgamation with it. Therefore, when we say threshold voltage, it is that threshold voltage that we had discussed earlier when we studied MOSFET. That is, it is that value of the voltage, VTH, we had studied. Remember, it is
Yes,
that
ma'am.
value of threshold voltage which is required to be applied in order to complete building up the N channel. That is this induced layer of channel, so that you get a very dense inversion layer, you get the inversion point, and after this only there will be sufficient accumulation of inversion charge or negative charge on the metal semiconductor interface that will actually induce that N channel. Physically in that structure, remember, initially
No
we did
channel
not
was
draw any
present.
N channel, but later no N channel was present, then later we induced it. So
Yes,
that
ma'am.
inducing process is basically what we did it in the previous class. But how it is done and how the inversion layer is created and what is the condition for setting up that inversion point and threshold voltage is what we discussed today with the MOS structure and energy band diagram. Clear? দুটোকে correlate করতে পেরেছো তো? মানে
Yes, ma'am.
students
Yes.
মানে আগের দিন যেটা আমি পড়েছি, that's the phenomena which takes place, how current flows. But today what I am discussing is just the MOS part, because that is the heart of the entire MOSFET. And next class also we would continue with the rest of this chapter. You can go through in this chapter. It is I have taught you pages from the starting page, from pages 427 to 434 is what I taught you in the hard copy. Okay, you can refer to the soft copy also. That would be chapter 11. So I had actually taught you up to article 10.1.2, that would be 11.1.2 in your soft copy. We continue with it tomorrow. Clear, students? Class
Okay,
would
ma'am.
almost end. If you have any queries, you may ask. একটু পড়ো আজকে যদি পারো, বা tomorrow, I don't know whether you get just coming back before to the next class. Tomorrow's would be a little more complicated. So just go through Neiman. These pages have a reading. I think after today's explanation, if you just go through it, things will become very clear to you. কালকে বুঝতে সুবিধে হবে, না হলে কালকে বুঝতে অসুবিধে হবে। Fine.
Okay, ma'am.
আমার কিছু বলার নেই। If you have webex would end in maybe next 5-6 minutes. যদি তোমার কিছু বলার থাকে বলো, আর না হলে আমি মিটিং এন্ড করে দেব। It's already 7:30. Sunday I won't be penalizing you anymore, and thank you for attending a class on Sunday. Thanks to all of you. ঠিক আছে তাহলে, okay, go and have your tea and coffee. It's time for a coffee break. Thank you. Ending. Okay,
Thank you, ma'am.
thank you.
Thank you, ma'am.
Thank you.